welcome to the video for Unit 7, Lesson 7, Bond Enthalpies. This is for AQA AS Chemistry. The lesson objectives for this lesson are to be able to determine mean bond enthalpies from given data, and to be able to use the mean bond enthalpy to calculate a value for delta H for simple reactions. First of all, we need to do a quick bit of revision from GCSE. So in GCSE, you would have learned about exothermic and endothermic reactions. So exo, you think of EX as being exit, so going out, and we all know that the word stem therm, it means to do with heat. So exo, X from exit, and therm from heat, that's the heat going outwards. So an exothermic reaction is one which gives out heat, and the heat escapes and heats up the surroundings. An endothermic reaction then is the opposite. So if you think about En as in entrance, and again therm as in heat, then that's heat coming in. So in an endothermic reaction, the temperature goes down because the chemical system takes energy from the surroundings, usually in the form of heat. So at GCSE that was almost enough. We did talk at GCSE about the relative strengths of bonds being made and bonds being broken. So in an endothermic reaction, that chemical system is gaining energy, it's getting energy from the surroundings, which means the bonds that you're breaking are stronger than those that are being made. So it takes more energy to break the existing bonds than it does than the energy that you get out in the end. So when you're making and breaking bonds, so first of all, in your reaction you're breaking bonds, and then you make new bonds in your products. So in an endothermic reaction, the energy you put in to start with, you don't get as much energy back when you make the new bonds. The ones that you're breaking are stronger than the ones that you're making. Exothermic is the opposite. So the bonds you're making are stronger than those that you've broken, which means the energy you get given out when the new bonds are made is more energy than what you had to put in to break bonds in the first place. So overall, you get more energy being given out, whereas in endothermic, you have a net loss of energy, so the energy has to come in from the surroundings. So now we need to think about how this goes towards AS level chemistry. And what we're talking about today is bond enthalpies. Now, bond enthalpies are a measure of how much energy is required to break different bonds. So, if you've got a stronger bond, you're going to have a more positive value. So the bond enthalpy, the higher the bond enthalpy, the stronger the bond is. Now remember, breaking bonds is endothermic, so that's going to require energy. And if you make bonds, that's exothermic, so you're going to give out energy. So if you've got the same bond, if you break it, and then if you make the same bond, then it's going to be the same amount of energy that's involved. It's just that the signs are going to be opposite. So you remember from previous lessons, if you're giving out energy, that's exothermic, that's going to be a negative sign. So if you're making bonds, then it's going to be a negative enthalpy. If you're breaking bonds, that's going to be a positive enthalpy, because you've got to take in energy from the surroundings. But if you have a given bond, like a HH bond, it's going to take the same amount of energy to break the bond as the amount of energy that you would get out if you made that same bond. So all that's different is that the sign is opposite. So to break it, it's endothermic, which is going to be positive. To make it, it's going to be exothermic, which is negative. Now, the important here is about the difference between a bond enthalpy and a mean bond enthalpy. So some bond enthalpies can only ever have one value. So for example, HH, you only find the HH bond in a H2 molecule. That is the only place you can have it, because a hydrogen can only have one bond, so therefore a HH bond, there's no other spare bonds that can be joined to any other atoms, so it's always going to be a HH bond can only be found in one place. It can only be found in H2, so it's going to have a distinct value. So the HH bond is going to have a very specific bond enthalpy. However, if you've got something like a CH bond, there are thousands, if not millions, of organic compounds which have got the CH bond in, and they're all going to have different values, because the strength of that bond is going to be affected by what else is on that carbon, what else is in the molecule. Everything's going to have an effect on it. So every different compound with a CH bond in, that bond enthalpy is going to be slightly different. And in fact, within a molecule, if you've got different CH bonds in different environments, you're going to have different bond enthalpies within the molecule. So the values are influenced by the environment, which is just said. And for these ones, because we don't want to measure the CH bond in every single different environment, we have, or we use, average bond enthalpies, which means we find out, so for example, a CH bond enthalpy over a range of different compounds and average it, and that gives us a useful value that we can use in calculations. However, it does mean that there will be a difference between experimental values and theoretical values for something like a CH bond, which can be in many different environments. So the all-important definitions which you need to learn. So bond enthalpy is the enthalpy change that takes place when breaking by homolytic fission 1 mole of a bond in the molecule of a gaseous substance. So it's got to be in the gaseous form, and it's got to be homolytic fission. Now, there's a difference between homolytic fission and heterolytic fission. You don't need to worry about it too much, but what it means is when you've got homolytic fission, the two electrons in the bond will go to different places. So even though it says homo, and you might expect that the electrons will go to the same place, what it means is that the fragments you get are the same. So instead of in heterolytic fission, you'd end up with a positive charge and a negative charge, because both the electrons will go onto one of the atoms. In homolytic fission, the electrons go to different atoms, and therefore you end up with two radicals. So in this case, we've got a chlorine molecule. One electron goes to one chlorine, and the other one goes to another chlorine, so you end up with two chlorine radicals. So the second definition is very similar. It's just the mean bond enthalpy. So the mean bond enthalpy is the enthalpy change that takes place when breaking by homolytic fission 1 mole of a bond in the molecule of a gaseous substance, averaged over a range of different compounds. So it's just that last segment, averaged over a range of different compounds, which is important. And that's missed off in a lot of exam questions, so make sure you include that if you're asked for a definition of the mean bond enthalpy. So what we're quite often trying to work out in these sort of questions is the delta H, or the enthalpy change. So what we need to realise is that the energy required to break bonds in a chemical reaction are going to be the sum of the bond enthalpies of the bonds broken. So if you add up the bond enthalpies of every bond that you're breaking, that's going to give you the energy required to break all of the bonds together. Likewise, if you can do the same thing for the energy required to make the bonds. It's going to be the sum of the bond enthalpies of the bonds made. Then the overall energy change, delta H, is going to be the sum of the bond enthalpies of the bonds broken, take away the sum of the bond enthalpies of the bonds made. Now, if you think about your signs for your exothermic and endothermic, this makes sense. So an exothermic reaction, we've talked about as having a negative enthalpy. And we've also talked about at GCSE level that if you've got an exothermic, that means the bonds you're making are stronger than the ones that you're breaking. So if you look at this calculation, that's quite obvious, because if delta H is the sum of the bond enthalpies of the bonds broken minus the sum of the bond enthalpies of the bonds made, then if the bond enthalpies of the bonds made is bigger than the bond enthalpies of the bonds broken, you're going to have a negative value. Likewise, if it's endothermic, you're going to have a positive value for delta H, which means the bond enthalpies of the bonds you're breaking is going to be more than the bonds that you're making. Now we need to look at an actual example. So here's an example where you've got methane, which is CH4, reacting with oxygen to give carbon dioxide and water. So if you look at the left-hand side, we've talked about you've got to add up all the bonds that you're breaking. So you've got to add up the bond enthalpies of all the bonds you're breaking, and on the right-hand side, you add up all the bonds that you're making. So if you look on the left-hand side of this, you can see you've got the reactants all drawn out. You've got 4 CH bonds there, so the methane's got 4 CH bonds. You need to break each one of those CH bonds, and you need to break both the 2 OO double bonds. So you've got 2 OO double bonds to break, and you've got 4 CH to break. And on the right hand side, you are making 2 C double bond O's, and you're making 4 OH bonds. So it quite often helps to draw out the structures in this way before you tackle a problem, so that you can make sure that you're including all the bonds that are being made and broken. Okay, so if we write this out in a calculation, it would be like this. So for the reaction CH4 plus 2HO2 to give CO2 plus 2H2Os, we're given the average bond enthalpies breaking the bonds. For CH, it's plus 413 kilojoules per mole. For O2, a double bond, it's plus 497 kilojoules per mole. And for carbon oxygen double bond, it's plus 805 kilojoules per mole. And for OH, it's plus 463 kilojoules. So remember, if you're making the bonds, it gives the same number, except it's going to be negative. So the bonds we're making are 4 CH bonds and 2 OOs, as we saw on the previous slide, and the bonds we're making are 2 carbon double bond oxygens and 4 OHs. So if we plug these figures in to our previous equation that we had, enthalpy change is the sum of the bond enthalpies and bonds broken, take away the sum of the bond enthalpies and bonds made. We then put all those figures into that, and you end up with minus 816. So as you can see, the bonds you are breaking there are weaker than the ones you're making, therefore you end up with a minus figure. Now, there are some shortcuts you can make for some of these calculations. So not for the one we've just done, but for this one, for example, if you're adding hydrogen H2 across the ethene, the C double bond, the carbon, then going from the left to the right, there are some bonds that are not being broken. So what you could do is the same as what we've done on the previous example, where you could say, right, that on the left hand side there's 4 CH bonds, there's a carbon-carbon double bond to break, and there's a HH to break, and then we've got a carbon-carbon single bond to make on the right hand side, and we've got 6 CH bonds. That will give you the correct figure if you do it, but it's more work. As you can see on the next slide, what we can do is we can have shortcuts. So what you can do, you can just look at the bonds that are being made and the ones that are being broken. So if you look on the left hand side, the bonds that I've highlighted in red are the ones that are being broken. Because if you look at those 4 CH bonds on the left hand side, they're still there in the right hand side molecule, so you're not actually breaking them. So the only one that you need to break in the ethene is the carbon-carbon double bond. And then in the H2, you've got to break the bond between the HH. So we could just do a sum where we just, for the bonds broken, you would just include the carbon-carbon double bond and the HH single bond. And then for the ones that you are making, you're making 2 CH bonds, because although we've got 6 in the final molecule, 4 of them were already there to start with, and you're making a single carbon-carbon bond. So the reason for doing this is just it's simpler, it requires less figures going in, and which means you're less likely to make a mistake. So it's up to you which one you do, just make sure you don't do a mismatch of the two. So either list all the bonds being made and all the bonds being broken, or just look at the ones that are being broken and made. Best thing to do is to have go at a few examples yourself and see which method you prefer. So let's go over our lesson objectives. They were to be able to determine mean bond enthalpies from given data, and to be able to use mean bond enthalpies to calculate a value of delta H for simple reactions. So if you feel you can do these now, that's great. If not, then either rewatch the video or have a look at textbook or do something to make sure you understand it.